So next up, we have Pavel, who is going to be talking about how Tableau has been doing a lot of work in making big data be accessible through visual query. So, Pavel.
Good morning, everyone. So Tableau is at heart a data visualization company, not data processing company. However, for the past 5 years, I've been watching how the need for data processing and Tableau has been growing. And today I wanted to talk to you about what it means to do data processing for visualization and about some recent improvements that we made in version 9. That release was mostly about performance. So everything started at the beginning of the century with the system Polaris, a research project, original idea from our co-founders Pat Hanrahan and Chris Stolte. And there's a lot of commonalities between this original system and the Tableau you see today, even in the visual interface we have. So every single interaction in Tableau follows the following workflow. We start with user interface, and user is operating on some components from a data model that is built on top of metadata of data sources we connected to. And we specify what we want to see. Then this specification is interpreted, and eventually we get a display. There are a few things that are important to understand about this model. One is the separation of what we want to see, the actual data, and the graphical encoding of this data. In fact, the application will suggest that for this particular columns, for these measures, you can use these kinds of charts. Another thing that is important and definitely contributed to our success and to success of Excel and many other applications is the use of tables. People understand tables. So the tabular data model is the input, and we work also with multidimensional models, with specialized data sources. However, we always try to tweak them to work with this approach. It's maybe less obvious that we are using also tables on the other end for the display. One of the novelties of the Polaris system was to define an algebra over columns from the data source to define how graphical displays are composed against every single axis. So over years, the data requests became more complicated. At the very beginning, with Polaris, you could do filtering and aggregation, obviously. But now there is a lot of rich analytics. You can blend against different data sources. You can do forecasting. You can integrate with language R. One of the recent improvements is level of detail calculations. You can do, for example, cohort analysis. We can join data with a lot of different levels of aggregation for a single visualization. So that's one of the dimensions for us. The data requests are much more complicated. The second one is scale. Today we are reaching over 1 million users across 30,000 accounts. And that's users that are actually doing analytics, very complicated tasks. Another dimension could be data volume, but not really, because we are about interactive data visualization. So if we connect, let's say, to Hadoop, we can do a static report. But we don't have this experience that we want to provide our customers with across the board. That's why, yes, over years we are handling more and more data. But there is a clear distinction between the sets that we can support and the sets that we have to extract and we need to work on a subset. There are two major tasks that our customers use Tableau for. One is data exploration, when you start with an empty canvas and you actually want to understand your data set. So you usually follow some unique path and you pick columns without really understanding the physical model. And that really affects systems that, let's say, scale out, because it really depends how the data is partitioned. And nobody cares if we are picking the partitioning column or not. In this case, it's also hard to come up with good strategy for caching, for data prefetching, because a user can do anything. Once we understand our data set, the next task is to share our discoveries with colleagues, with the world. So we built bigger units. In Tableau, you can build dashboards, you can build stories. Here, the workload is very different. It's usually not a single or a few queries. It's 50 queries, 100 queries per interaction. Also, you can think about a dashboard as a set of stored procedures. It's parameterized. It's always the same fixed structure of queries. There are dependencies between zones. So sometimes you need to wait for the results from one zone to get to formulation of subsequent queries. But it's much easier to address this case with caching just because of this fixed schema. Also, the target is very different. It's not a single user, it's multiple users. So caching is critical. Let's look at an example. It's a pretty simple dashboard against one data source, a very popular benchmark in data visualization, a database of flights in the United States in the last 10 years. We have two maps that we can use for filtering. They show at different locations delays and numbers of flights. There are additional filters on the right-hand side and some detailed slave visualizations below. So there's no complicated analytics here. Again, this is just aggregation and filtering. The thing that we can expect from this dashboard is a lot of queries, maybe some interactions between zones. And I wanted to show you how this dashboard performed in Tableau 8, so in the previous release. And it's 150 million rows of data, everything happening on a MacBook Air, a single laptop. The backend is also the same laptop. We'll see two prevalent operations. One is the computation of the layout. This is when we already have the data and build the visualization render. And the second one is query execution. And we'll see that the second interaction, when we try to restrict the data just to April across all the 10 years, sends a lot of queries. And I think this whole interaction will take 25 seconds. So next time when you think of, let's say, looking at March, you'll think twice. Every user can generate a Gantt chart of the performance recording for any period of work with Tableau. So in particular, here we are looking at execution of queries. We captured exactly this scenario that I just showed you. And we see that zones that are referred here as worksheets, we're sending a lot of queries. Well, that's the first observation. There's a lot of short queries. Is there any redundancy here? Can we do better? Is this something that we really have to run for this visualization to compute? Second thing, there's no overlap between queries. So they are running serially. Isn't that silly? Can we do better? Would that help if we run them in parallel? The gaps between the queries on the x-axis, on the time axis, is the computation of the layout. And we are not talking about it today. So 3 questions that I will try to answer, and 3 questions that are very important for us in data processing. Can we run fewer queries? Can we run them in parallel? And then eventually, if we work with an external backend, can we build better queries, SQL of better quality? If we run against our own backend, can we make the backend faster? So first, I wanted to talk about fewer queries and running in parallel. That's an improvement that we added in version 9 and was actually critical for performance. Well, users don't think about queries. For them, a computation unit is the whole dashboard. They made an interaction. They want to see a complete result. We try to think in exactly the same way. So every single zone in this dashboard will have some data requests. And now if we want to run those requests in parallel, we cannot simply send them to the backend, Because given that we have caches, the order of this operation will matter. And some of the queries maybe will be sent to the remote database. In the other scenario, they won't be. That's why first we bring them all together and you have an initial stage when we analyze the data. So this is pretty much multi-query processing. This is something that the backend will not do for us. Backends don't think in terms of query batches. They just look at first come, first served. We use a matching logic from our intelligent cache, and this is pretty much the view matching logic. And we can identify that some of the queries can be computed from the results of previous queries. Like in this case, query 8 can be computed from query 3 or from query 4. So given those dependencies, we can run them in parallel. But of course, query 8 will have to wait either for query 3 or query 4 to compute. Another optimization that we do across queries is very simple. We realized that customers build dashboards when zones share exactly the same relation. They share the same filters. But they want to show different measures. They want to show, let's say, arrival delays and profit and expenses. So we can bring them together to a single query. And in most cases, this query will be more efficient than running independent queries. So how the picture changed now in version 9 when we started batching queries together and running them in parallel? Well, we see that there are fewer queries. So that's one benefit. Second thing, queries are running in parallel. Again, success. The problem is that now the queries, comparing to the previous Gantt chart, are much longer. And we need to understand that this is because there are not only that many resources on the box that we are using. We were running against our own column store that was sitting on this box, and we just didn't have enough computation power to provide to all the additional queries we're sending in parallel. There are also some queries that waited for execution. As I mentioned, not everything can be batched together right away. So what does it mean to run queries in parallel? Well, actually, the model for databases is to open independent connections. There are only few databases that allow you to send queries against the same connection. For example, SQL Server with Mars. But even in our experiments, all those databases were taking a performance hit when we were using those solutions. So today we support over 40 different connectors. And that means that we need to provide a solution that will work everywhere. So we started opening more connections. And the multiplier in version 9 is 16. So when our customers switch to version 9, suddenly they open much more connections. And some of the backends were really happy about it. Some of them actually were throwing exceptions. One of the examples would be Redshift. Redshift will complain that we have too many active cursors open. And that's a surprise because the database server should be able to handle a lot of concurrent users. We learned a lot from this improvement. We had a chance to work with customers as we were going forward. We worked with Facebook, we worked with Google, we worked with Unilever in Europe. And findings were very different depending on the architecture of the backend. For example, very successful with Google, where you have 3,000 machines waiting for your queries. And we were able to go from, let's say, 2 minutes per query, 2 minutes per dashboard in version 8 to just 5-10 seconds. So that was a huge improvement. That was an order of magnitude. But there were cases where we would deploy our solution and there was no difference, or there was a regression. And it turned out that there's a lot of defaults that limit the throughput of the data source. Let's say on Vertica with default resource pools, we had problems with the number of concurrent queries that can run in the system. And in this case, we really had to do investigation. We really had to wait with DBAs to understand what was happening. Also, if you think about it, if you have an MPP architecture that scales perfectly, well, then it doesn't matter. You can send queries serially, you can send them in parallel, and you should get exactly the same performance. But of course, it's impossible in practice, and it really depends on the type of the queries you have. Not all of them will scale across all your resources. And this is what we take advantage of here. As I mentioned, databases don't really take advantage of the fact that we are sending queries together. Well, there is some scheduler, there is some queue of queries. They will be throttled on the backend side, but there's no way to send the whole query batch and say, this is what I'm interested in, and please allocate resources wisely. Those resources will be regained as the queries come. One of the optimizations that we see useful, for example, in SQL Server are shared scans, where we actually share something across queries, cooperative scans in MonADB. So that was about fewer and about in parallel. Now I wanted to talk more about the quality of the queries, where we work with different optimizers in the backend. So we try to cover all the deficiencies of their optimizers. In particular, we do joint calling, we reduce predicates, we actually try to fetch domains to make the expressions simpler. All the common suspects in query simplification. Sometimes we go further than optimizer would go because we understand the workbook. We know that some of the filters, let's say, have thousands of elements, but we'll be reusing them across interactions. We'll materialize them as temporary tables. Another example would be agreeing to some differences in semantics or precision of the results. We can say, well, this widget actually doesn't need all the data precisely, and we can call joins and just get the data from the dimension table. That's a huge change for performance, and we can only do that because we said so. The fact that we support that many connectors, it's not only talking to their drivers, it's also discovery and understanding of the capabilities. It's also understanding the library of functions they have. Let's say we have date truncation. We can create a complicated expression that will run really slowly on every single database. Or we can realize that, well, this database actually supports that. So there are hundreds of cases like that because, well, Tableau is mostly about the richness of analytics. Caching. Caching is important. I mentioned the intelligent cache. This is how we send fewer queries. We do operations like a local rollup, local filtering. And again, because we do something locally and maybe the collation on the other end is different or maybe not matching perfectly, we might get slightly different results. And actually, in many cases in visualization, that's OK. People more care about this interactive experience. This is the most important cache related to query processing for us, so we distributed this cache in the whole cluster. In the cases when we cannot prove that some of the queries actually can be computed from the results of the cached queries, we have the literal cache that just uses the query text as the key. We use it also for MDX, for special cases, for metadata. Now I wanted to talk about the very first project I was working on when I joined, our own column store. Well, every company has now a column store. Why do we? Well, originally Tableau was able to work live with backends and only live. And that's fine when customers have strong analytic backends. But in all the cases when the backend is overloaded or is just not made for analytics, or we work offline, or it's Hadoop and the latency is just too high and you need to work on a subset of the data. For all those cases, we needed our own engine. This engine works on small amounts of data relatively, comparing to, let's say, Presto, Google BigQuery. It will work up to 1 terabyte. We use it for local processing that is sometimes not available to the user. We do it internally. It's also a foundational element of our cloud offering, Tableau Public or Tableau Online. All the data that customers send to us is in the format of this data engine, and we process this later on our end using this data engine. The architecture is based on MonadDB and on CStore. So it's block iterated. We optimize for the workload coming from Tableau. We have a lot of complicated expressions, so the vectorization of functions was very important. We use strategic and tactical optimization, so you can see common sub-expression elimination, you can see push down of operators, various simplifications. We use compression a lot, of course dictionary compression, but on top of that we use different types of encodings. And we deploy the same code base in both environments, on the desktop for a single user and also in the server environment. And on the server, we do not partition data, we don't scale out, we have independent instances, we either share nothing, we replicate the data, or we share a single powerful SSD device or disk. So because we have those two environments, the strategy for us today is to scale up first. And we had some prototypes of scaling out. However, there's no really strong use case for us, no need from customers to go forward in this direction yet. And one of the examples from version 9 that helped a lot with scaling up and kind of competes with opening multiple connections, competes over resources, is to use parallel plans for individual queries. Nothing new. It's a classic exchange model, local global aggregation. Then we use it for parallel scans. We use it for expensive computation. Another thing that is maybe quite maybe not unique, but not that common in column stores, is enabling the optimizer to understand compression. And we actually expose it to the optimizer through tables. The compression of the data for a dictionary compressed column is just simple join. We also introduced a new type of indexes for columns that are RL encoded. So we built an additional table, and again, we give it to the optimizer. We use a range join in this case to implement a skip scan. And just the fact that we see those tables in optimization allows us to do a push down of computation, to do a push down of filtering, so pretty much to work on compressed data. And now to finish up, a few words about Tableau Server. Just a few components of what is deployed on boxes in the cluster to support our system. vSQL Server would be an equivalent of some components from Tableau Desktop. So actually, this is the process that is generating visualizations. We have usually a bunch of processes like that on every box in the cluster. Then I already talked about the data engine. We have a few instances in the cluster. And then wanted to move for a little bit to the data server. That's a fairly new component comparing to the rest of the product. We introduced it because Tableau is not only about data visualization, it's also about creating rich data models. And data server is a component that allows you to share those models. So in particular, if you have a single account in the backend and you want to build your own hierarchy of users, your own permission model, you can use the data server to publish this connection and then allow other people connect to this published data source as it was another database. This way you can also share the formulas that you defined, make sure that they are consistent across workbooks that you create. This way you can also share extracts. Once you create an extract, you don't want to maintain the same copy in multiple workbooks. You don't want to store it multiple times. You can share it through the data server. Well, that brings some problems to the architecture, because now you have this additional proxy that is between your client, so either the desktop application or a process in the server, and your database. And the client now doesn't really understand the full data model. For example, it cannot do join calling, right? So we made sure that the same query processing pipeline is used also on the data server. So the processing will happen twice in a limited way on the client side. And then after the model is expanded, fully understood with permissions applied for a particular user, we will do proper processing on the data server side. Then the only cache that is available here is a literal query cache that works with query text. So we made sure that this cache is also distributed on the cluster. And last but not least, I mentioned a few times that temporary tables are important. We create them for multidimensional filters, for large collections. We use them for certain functionality like blending across data sources. We make sure that those structures are persisted and we don't have to send them every single time at every interaction. So we added this functionality to the data server as well. And we can actually support temporary tables on the data server or from the data server in the backend, depending which connection actually has higher latency. And I'm allowed to talk about one pretty modest deployment of our architecture, Tableau Public, that actually launched also around 5 years ago when the data engine started. It's a public gallery of interactive visualizations. You can open an account. You can create visualizations for free using Tableau, publish them to the web, use them in your blog. Today, we have over 100,000 authors and over 500,000 of visualizations. And this number is growing more and more now. So to support a system like this, note that we actually don't give that much storage per author. So the data that we have to process is really not that large. To support a system like this, we use just 2 instances of the data engine. We use 25 boxes with processes that generate visualization. Great. So that was an overview of how we do query processing and what challenges we have with different backends in Tableau, and a few areas that we are exploring currently. Thanks much.
Have time for maybe a couple of questions.
Yes.
So I have a question about the column store that you have built.
Yes.
Is this a pure read-only? You load once and you query forever, or you update, or?
Yeah, it's a read-optimized column store. You can append to the extracts. So you can define a refresh schedule and get new data, but you cannot do point updates.
So you eventually, effectively, you load after a certain amount of time, like if you have new data coming in, right? So if you want to update the column.
Yeah. Depending on the refresh strategy, yes, you will be appending to the same extract. I should have mentioned that it's memory bias. It's not fully in memory, so we will always page through the extract. We don't rely on having a lot of memory on a laptop, for example.
Okay.
Hey, Pavel.
Hey, Jose.
So for the accelerator that you guys are building for the small data sets, 1 or a few terabytes, did you consider using one of the backends that already supports column store as a way to kind of accelerate you?
Yeah.
And save on that investment?
That's a great question. So originally, actually, the extract feature in Tableau was delivered using Firebird. And it was not because Firebird was fast. It was because it actually supported some of the features we needed, like per column collation or some of the analytic functions. Then we realized it's too slow. We looked at MonadDB. That's a research project. We are actually friends with people from CWI. And they were asking, like, hey, this is a general purpose database. Try it. Well, the database wasn't just there yet. For a while, we had a way to use any database as an extract engine. We had a few customers that were, for example, using Vertica for this purpose. But again, our customers were mostly into 2 groups. Either customers that had analytic strong engines and they were just using them. They wouldn't even use our extract engine. Or maybe they would use it behind the scenes, but that was for small volumes of data. Or they just didn't have anything, but they didn't really have that much data either. So at that time, there was no good solution for us. So that's why we built something. Today, maybe the situation would be different. Maybe we would make other choices.